Okay, so we are in section 7.4. This is called integration of rational functions by partial fractions. That's quite a mouthful. Most of the time, we just call this partial fraction integration. But it is exactly what it says, integration of rational functions by partial fractions. In other words, in order to use this, you need to have a rational function. What is a rational function? Let's go back and remember what that is. A rational function is a polynomial divided by another polynomial. So in other words, this does not work if you have an exponential over top of a rational function, or it doesn't work if you've got a natural log in the fraction somewhere. It has to be a rational fraction. All right. In order to understand what's actually happening here, let's start off by combining two rational functions. So if we had 2 over x minus 1 minus 1 over x plus 2, just like with any other fraction, you'd need to have a common denominator in order to add or subtract the two fractions together. Well, in this case, we need to get the common denominator, which is just going to be a multiplication of the two linear denominators, x minus 1 and x plus 2. So we know that the denominator is going to be x minus 1, x plus 2. I'm not sure that that really looks like a minus 1 in there. X minus 1, and then x plus 2. And then we're going to also have x minus 1, x plus 2. In the second denominator. So what do we have to ask ourselves, what did we need to make the first one, that 2 over x minus 1 with the common denominator? Well, you need to multiply the top and the bottom by x plus 2. So we'll write that in, which means now we're going to get a 2 times x plus 2 on the top of the first one. And then we would need to multiply the top and the bottom of the second fraction by x minus 1. So we're going to get 1 times x minus 1 on the top of the second one. And then we can go ahead and distribute everything on top and combine the fractions. So we're going to get a 2x plus 2. Don't forget that negative sign gets distributed to both things here, so that's going to give me a minus x and a plus 1 over our common denominator, x minus 1, x plus 2. And then going ahead and just combining like terms on top, we're going to get 2x minus x is x, 2 plus 1 is, silly mistake. That is not a 2, because I forgot to distribute the 2 to both things on top. That's a 4, so we get 4 plus 1 is 5. And then you could go ahead and distribute this out. Let's go ahead and do that. That would be x squared plus x minus 2. And what you should notice is that in the next sentence, I have exactly that function that I'm integrating. So it follows that if I wanted to integrate what we just got here, if I want to integrate this, because that's what this is right here, if I want to integrate that, we can rewrite the integrals as the integral of 2 over x minus 1 minus 1 over x plus 2 dx. And the question might be, well, why would I need to do that? Well, if you look at the original function, this one right here, that we have when it's not in its separated form, we don't have a method to do that yet. That's what this is establishing. This is giving us a method to undo what would basically be this quotient rule here. We're not really undoing the quotient rule in this particular case. We're actually undoing log derivatives for the most part. We are going to have some other things in there, but mostly this is log derivatives. But you can see that now this function right here, when I integrate, both denominators are linear. And when you have a constant over a linear function, the antiderivative is a natural log. So the first one, by taking the antiderivative, would be 2 times the natural log of the denominator, x minus 1. Don't forget it's an absolute value. Very, very important. Don't lose the absolute value. Minus 1, I don't have to write that, times the natural log of the absolute value of x plus 2 plus c. So from this form, it's very simple to go ahead and take the antiderivatives. Of course, they will get a little bit more challenging when the denominators are not necessarily going to be linear, or the numerators don't always happen to be constants. But in order to do this, what we need to do is say, okay, well, how would I have gotten from this back to this? If we start off with that rational function, how am I going to separate that into two things where I can do the natural log antiderivatives? Well, this is what is called decomposing a function. Okay, so if we want to decompose the function, that's what we're going to try and do. There are a couple things we have to go through first before we can actually get to the decomposition part. In some cases, like in the one that I have down here, it may be necessary to take a preliminary step involving long division of polynomials. And the reason for that is this. If the degree of the numerator is greater than the degree of the denominator, which we have here, this is an improper form of a rational function. We need to get it into a proper form, which means that the power on the top is going to be less than the power on the bottom. The only way to do that is to go through a process which is long division. So in order to do long division, just like you would do if you had, 17 divided by 4, the 4 would go on the outside, the 17 would go on the inside, then you would perform your long division. Well, it's the same general idea. We're going to put our division symbol here. The x minus 1, which is the denominator, goes on the outside. The x cubed plus x goes on the inside. But don't forget, you have to have placeholders for everything that's not there. I don't have an x squared term, so I have to have a placeholder for that. Well, I don't have any x squared, so we just say it's 0 x squared plus x. And then technically, I don't have a constant either, so I'll put a plus 0 on the end there. Okay, and all that really does is really helps us to keep everything in the right placement when I go to do the long division. All right, reminder on long division. What we do is we look at this first term here and we ask ourselves, what do we need to multiply that x by to get the x cubed? Well, of course, that would be x squared. So that means that on top here, on top of my x squared term, I'm going to write x squared because that's what I need to multiply. Now you distribute the x squared to both terms, and then you write it down below. So x squared times x is x cubed. X squared times negative 1 is negative x squared. And I always do this next part. I put a parentheses and then put my subtraction sign on the outside of the parentheses so that hopefully you won't forget to distribute the minus sign to everything. Now it's x cubed minus x cubed. Well, that's 0. We need that to happen. The first term has to go away every time, otherwise we're doing something wrong. The second one is 0 minus the minus x squared, which is really going to be plus x squared. So that's going to be plus 1x squared. Just like you would do in other long division, the next step is to bring the next term down. So that's what we're going to go ahead and do. Bring down to plus x. And then we repeat the process again. We don't need to leave that 0 out here. You can if you want to, but don't confuse that because you don't need it. So the next thing says, okay, what do I multiply this x by to get x squared? Well, I'm going to multiply it by x. Okay, so there's the next term. So x times x is x squared. X times my negative 1 is negative x. Put the parentheses and subtract. X squared minus x squared is 0. X minus the minus x is really plus x, so that gives me a 2x. Bring down the plus 0. And then the last piece is what do I multiply times my x to get 2x? Well, that's 2. So now we'll distribute the 2, and we're going to get 2x minus 2. Parentheses, don't forget to subtract. 2x minus 2x is 0. 0 minus minus 2 is plus 2. We don't have anything else to bring down, so that's our remainder. So what that has done is that's given us plus 2 over x minus 1. So your remainder goes back on top of your original denominator. So now what we've done is we've created a way to integrate this. Whoops, I changed the color. a way to integrate this, because what we've done is we've, in a way, we've decomposed that fraction to make it proper now. So what we have is the integral of x squared plus x plus 2 plus 2 over x minus 1 dx. The first three are just your standard antiderivatives using the power rule. So we'll have 1/3 x cubed plus 1/2 x squared plus 2x. And then the last piece here, whoops, hit the wrong color there. There we go. That last piece, that's going to be a natural log antiderivative. Because, again, you have to recognize that's a constant on top of a linear function. And that's just going to be a natural log. So it'll be the constant 2 times the natural log of the absolute value of x minus 1. And then, of course, it's an improper, so don't forget plus c. All right, that's a decent amount of work to get to that, but that is one of our methods now to take antiderivatives. Okay, this is called partial fraction decomposition. So that was one way to start to decompose a fraction if you have an improper fraction form. Sometimes that doesn't fully do it. And if that's the case, sometimes you have things which you can get into proper form. Now, the next example is already in proper form, but sometimes once you get it there, you still have more work to do. The next one is in proper form because, and this is case 1, the denominator's power is higher than the power on the numerator. So it's in the proper form. But how in the heck are you supposed to do this? Well, this is where the actual decomposition process comes into play. What you want to do is you want to go ahead and factor the denominator as much as possible. So let's go ahead and do that. Let's rewrite this. We don't need to do anything with the numerator. Now, if it happens that the numerator factors into something that might cancel something out in the denominator, then you might have something going there. But other than that, in this case, it's probably not going to work out. So the first thing I can see is I can factor an x out of the denominator, which is going to leave 2x squared plus 3x minus 2. But I can factor that denominator even more. And as a matter of fact, I kind of need to, because what I'm really hoping to get are linear factors in the denominator. And that second one there is definitely not linear. But it does factor into 2 linear factors. So I'll still have x, that's linear. And then let's see, factoring this, that has to be a 2x and an x. In order to get the plus 3 in the middle, that's going to have to be a 2 and a 1. That's going to have to be plus. That's going to have to be minus. Again, I'm not going to go through the whole factoring process. That is something that we should be able to do at this point. But now you can see that I have 3 linear factors. And in this case, they are 3 distinct linear factors, meaning none of them are the same. Because you could have x times x. While we know that that's x squared, x times x are still 2 linear factors being multiplied together. I don't have that in this case. I don't have an x plus 2 times another x plus 2. They're all distinct. They're all unique linear factors, and that's good in this case. So now what we do is we say, okay, the original function that we were integrating was x squared plus 2x minus 1 over my entire denominator, which you could write in either form, because ultimately it's going to go away here really fast, equals. If I want to split this up, I'm going to have something over my first linear factor plus something else over my second linear factor plus something else over my third linear factor, because if I were to add those 3 things up, whatever we have, and then combine all the linear factors by common denominators, you'd multiply them all together, you would get the one on the left-hand side. The real question is, what do I put on top? It'd be really nice if I could just separate that and be x squared, 2x, and negative 1 on top. It doesn't work like that. So we have to put some kind of a variable up here to indicate we don't know what those are yet. So we put capital A, B, and C, and if it keeps on going, you use D's and E's and all kinds of other things. Typically, you won't find anything bigger than hopefully 3 pieces, at least not for what we're doing. So the idea is pretty simple. If I were to multiply both sides of that equation by the common denominator on the left-hand side is going to go away. And that's going to leave us with x squared plus 2x minus 1. If I were to multiply everything on the right-hand side by the common denominator, the two pieces that are missing from the a are going to be left over multiplied by that a. So in other words, I would have, if I want the common denominator over here to be exactly the same thing as it is on the left, it would be x times 2x minus 1 times x plus 2. I'm going to erase this in a second, but I'd have to multiply that on top as well. And if I do that, then the x part here is going to go away because I'm multiplying it by the entire, I actually completely messed this up and I apologize. I'm not multiplying it on the top and bottom because I'm not trying to get the common denominator. I'm just multiplying everything on the top because I'm multiplying both sides of this equation. Well, the x's here are going to go away, which is going to leave the 2x minus 1 over the x plus 2 times the a. So we get a 2x minus 1 x plus 2. Similarly, the same thing's going to happen with b. If I multiply b by the entire common denominator, x, 2x minus 1, x plus 2, the 2x minus 1s are going to go away, leaving you with b times the other two denominators, x and x plus 2. And that might be the easiest way to think about it at this point in time, just to make it go a little quicker, is I have to multiply the c by the missing denominators, which in this case is going to be x and 2x minus 1 because it already has the x plus 2. And you might be thinking, well, how is this going to help? Well, this is an equation, which means that it should be true for any value of x that we plug in there. And since that's the case, the first thing we're going to do is we're going to say, okay, well, let's let x equal some easy, convenient value that's going to make some of this stuff easier for us. Well, what if we let x equal 0? If we plug x equals 0 into here and into here, 0 times both of those things is going to go away. That's awesome. The b and the c are gone. Now I can solve for a. You do have to plug the 0 into both sides. If I plug 0, we're going to let x equal 0. If I plug 0 into the left-hand side, I'm going to get -1. If I plug 0 into the right-hand side, again, the b and the c term are going to go away, leaving us with just what we get when we plug in 0 into the a term. Well, that's going to be a times a -1 times a +2. So that's really going to be -2a. So now solving for a, I get that a is going to be +1/2, dividing both sides by -2. Let's do the same thing, but try and get a different value. Well, what else could we make go away? Well, we could make a and b go away very easily if we let x equal -2, because then if I plug -2 in here and -2 in here, those are going to become 0. That's nice. So let's let x equal -2. Now we do have to do a little bit of work here on the left-hand side. -2 squared is 4, plus 2 times -2 is -4, so that's 0, and we still get -1 out of it. And on the right-hand side, I'm going to get c times, let's see, -2. Plugging in the -2 into the parentheses is going to be -4, -5. So I'm going to get +10 c, I believe. And then dividing both sides by 10, we get that c equals -1/10. And then we still have to find b. Well, the problem is what we've done so far is, well, no, we can still do this because we could also let x equal, what would have to plug in here? Have to plug a +1/2 into there, and that's going to make a and c both become 0, or go to zeros because of the fact that those parentheses are going to be 0. So that's good. So let's let x equal +1/2. Let's see, on the left-hand side, we're going to get 1/2 squared, which is a 1/4, plus 1 minus 1, so that's still going to be a 1/4. And then on the right-hand side, I got to plug that into the b section because the a and the c parts are going to go to 0. So let's see, that's going to be a half times 2.5. 2.5 is 5 halves times another half is going to be 5/4. So we get 5/4 of b. Multiplying both sides by the reciprocal of 5/4, which is 4/5, is going to end up giving us 1/5. So b is 1/5. All right, a lot of work to get here, but from here it's actually going to be pretty simple. All we have to do now is substitute a, b, and c back into this stuff right here and then integrate. Because remember, that's what we're doing. We're decomposing this function right here to make it simpler. So we're separating these things. So let's see. We're going to take the integral of a, which is 1/2, over x. And yes, I do leave them like this because it'll be much easier to simplify in the end. Plus b, which is 1/5, over the 2x minus 1, plus c, which is negative 1/10, over the x plus 2 dx. All right, and if you haven't seen this next trick, you're going to learn a trick real quick here that should help. The first one's pretty straightforward. It's just a constant over a linear function x. So we're just going to get 1/2 the natural log absolute value of x. No problem. Second one is where the trick is going to come in. I've still got the 1/5. I'm going to have the natural log of 2x minus 1. But notice that the slope of the linear function in the denominator is not just 1 here, it's 2. When this happens, you always have to multiply the outside of the natural log by the reciprocal of that slope. So the reciprocal of the 2 in the denominator is 1/2. The reason for that is this is a shortcut to doing a u substitution. Really, what you'd have to do is a u substitution, let u equal 2x minus 1, and then you would end up with that 1/2 anyway. This is a shortcut. If you have a linear function, which is the composite piece, which is in this case is what it is, then you're going to end up multiplying by the reciprocal of that slope out in front. So again, the reciprocal of that 2 is 1/2, which is why it gets multiplied out in front. It only works if the composite piece is linear. If that was 2x squared minus 1, this does not work. Don't try it. And then the last piece is we're going to bring down the minus 1/10 natural log absolute value x plus 2. Don't forget plus c. And there is the antiderivative, or excuse me, the integral. So again, that's a relatively long problem. It's not horrible, but that's the process. And we'll go through it a couple more times in the next video.